So yeah, let me know when I can start.
Yeah.
Yes, you can start, please.
All right. Yeah, hi everyone. I'm going to talk about the Fock ZX calculus, which is a graphical language for continuous variable quantum computing. Yeah, unfortunately, I couldn't be there in person because I didn't manage to get my visa in time, so this has to be online. This is joint work with Leah and Stefano Gogioso, and we recently put out the preprint on archive. So if you're interested, you can find more information there. So first, I will introduce the graphical language for infinite dimensions, which is going to be a version of ZX calculus, and then I'll talk about how we can represent these simple gates that you encounter in continuous variable quantum computing as ZX diagrams, and then I will show that the calculus that I presented is already complete for the Gaussian fragment. And here the Gaussian fragment means the classical simulable part of CV. So like in analogy with Clifford plus T, this is like the Clifford part. And finally, I will describe two applications in quantum error correction and Gaussian boson sampling. So the qubit ZX calculus has two types of generators, the Z spider and the X spider. So here I'm using the green and the red instead of the white and the black notation, like the previous talk. So the Z spider, which is the green one here, it matches the computational basis state. So it has cat0 and cat1, and it will make sure that either all of the wires have either cat0 or all of them have cat1. And we can also have an extra phase. So the Z spider corresponds to the computational basis, whereas the X spider corresponds to the Fourier, the Hadamard basis. So to generalize the ZX calculus to infinite dimensions, we need to look at what kind of basis states that are available and and the ones that we care about. So in L2R, which is the Hilbert space for the continuous variable systems, the basis states that we care about are position, momentum, and Fock. So position are, so cat x would be any real number. So x is any real number, and we have cat x. And if you take the Fourier transform of the position, we get the momentum basis, which will represent with cat p. So both of these bases are continuous, but we can also have the Fock basis, which will be the discrete basis. So this would correspond to, instead of position and momentum, which is the phase space picture, the Fock basis would correspond to the number of photons that you have in the system. But there's also the relation between the continuous basis and the Fock basis that is given by Hermite polynomials. But yeah, we don't need to go into that. So we will try to define spiders based on these basis states. The first generator in the calculus is the Z spider. This Z spider corresponds to the position basis, and it will match the position basis states, cat x here. Now, we can also label a spider with a function f, and this function f is a function from real number to complex. So for every basis state, cat x, it will give a coefficient for that. Similarly, we can define the Fock spider, which is the discrete spider. So it will match the number basis, the Fock basis, and we can also label it with a function, which now goes from naturals to complex. And we will also allow for global scalar in our calculus because it's just very convenient to have that. Now, using the Z spider and the Fock spider, we can define the X spider. So the Fock spider diagonalizes the Fourier transform gate. So this diagram gives us the Fourier transform. And so if I have minus I to the n, that's a Fourier transform. If I have I to the n, that's the inverse Fourier transform. So we can surround the Z spider with the Fourier and inverse Fourier transform to obtain the X spider. So we don't need to have this as an additional generator. It just can be a simple notation. We also omit the labels on the spider whenever it's labeled by a constant function 1. So some more notation, we can describe cat x, cat p, and cat n using these diagrams. We also have this multiplier. So multiplier labeled by m simply sends cat x to m times x. So it multiplies the basis state. Another notation is the W node. So some of you might have heard about the ZW calculus, which is like a generalization of ZX, or not generalization, a variant of ZX calculus. And it has this W node, which is very convenient for us, especially for running in the Fock basis. So this is how we can define it. The diagrams don't really matter, but what's important is that if I input the Fock basis N1 to Nk, so imagine I'm inputting N1 photon in the first wire and Nk photon in the last wire, it will put all those photons in a single wire in the outputs. It will sum over all of those photons. And we also have extra coefficient, which makes the interactions nice. So what are the rules of the calculus? So first we have fusion. This is the simple one. We also have the basis copy rule. So if I input a basis state in the corresponding spider, it gets copied. And we also get a coefficient based on the function. Next, we have the bialgebra. So yeah, most people are familiar with the ZX bialgebra, but there's also a bialgebra between the Fock spider and the W node, as well as two W nodes. And lastly, we can have the scalar rule, which says that if there's a global scalar outside, we can simply put it inside the Z spider where it multiplies the function. Right. So this might be slightly unusual, but all this is saying is that if you have that spider labeled by a function, you can change it. So it has to be only one output Z spider, so just a state. You can change it to an X spider by simply taking a Fourier transform of the function. And going from X to Z is the inverse Fourier transform. So in analogy with this, there's also a way to go between the Z spider and the Fock spider, and that's via the Hermite transform or the inverse Hermite transform. These are the rules of how multipliers interact. These are quite familiar from QDITs. And we also need to be able to remove a scalar one. We also have this Euler rule. So if you have a rotation gate, which is Fock spider label e to the I theta n, we can decompose it into Z, X, Z rotations. And here, this is just a rule saying there are two different forms of splitter, and they are equivalent. And finally, this is the most interesting rule, which is the triforce. So if you have three W nodes that are all connected to each other, it's same as the Z spider. And this also generalizes to arbitrary arity. So if you have W nodes that are more W nodes that are all connected to each other, that's same as Z spider as well. Okay, so this is a quick introduction to the calculus. Now you can see how gates are represented. So the first gates that we are interested in are the Gaussian gates. So the gates that are analogous to the Hilbert gates on a single node. So for that, we have the displacement, which is simply shift in the X and shift in the put together. We also have squeezing, which simply corresponds to a multiplier. And finally, we have rotation, and there are two ways of writing this rotation based on the Euler rule. Next, we can look at the two-mode gates. So these are entangling gates, and these three are still Gaussian. So first, we have the control naught, so C naught gate, and there's also an extra parameter that we can have, which is the S. And in the case where S is equal to 1, this would be like the this would be closer to the QDIT C naught gate. There's also the control phase gate, and when again S is equals 1, this is the usual control Z gate. And finally, you have the beam splitter, and there are two ways of drawing this beam splitter. This beam can be implemented with linear optics, and usually it's very easy to do. Now, to enable universal quantum computation, we need at least one non-Gaussian gate. And usually that's the cubic phase gate. And it's called cubic because it's e to the I gamma x cube, and where it's a function of x. We also have different non-Gaussian gates, like there have been proposals to use Kerr gate, which can be represented as a Fock spider, or an entangling non-Gaussian gate, which is the crosshair shown here. We can look at the completeness for this Gaussian fragment. And first of all, what is a Gaussian fragment? So we'll say a Gaussian fragment of our calculus corresponds to diagrams that are generated by these three diagrams. So we have a Z spider, where we can have e to the I pi, a linear part and a quadratic part. So ax plus bx squared. And we will also have the x spider, where we can have ap plus bp squared. So just linear and quadratic part. Along with this Z and x, we also need to give we also need to allow for vacuum state, which is a Gaussian state. And any diagrams that are generated by this is universal for Gaussian fragment. And to prove completeness, we rely on another calculus, which is the graphical symplectic algebra, which was mentioned in the previous talk as well. So this is a recent work by Booth, Carrett, and Comfort, where they showed that you can give these generators and give their semantics in terms of relations instead of linear maps. And they proved that these set of rules are complete for Gaussian quantum computing. So to prove completeness, we show that there is a translation between our Gaussian fragment and their calculus, which is invertible. And we can derive all of their rules using axioms of our calculus. And there's also more subtleties that I'm not talking about right now, but yeah, this is the main idea. And using this, we have the completeness. It says that if there are any two diagrams that are Gaussian and they correspond to the same linear map, then there is a proof in our calculus using the rules that I presented before that allow you to go from one diagram to the other. Okay, now let's look at two applications. So first is quantum error correction. So in quantum error correction, what you usually want to do is you want to represent your logical qubit in some physical system. So one way of doing this is with the GKP code. And in GKP code, you represent the ket0 as a sequence of Dirac delta that goes from minus infinity to plus infinity, and these Dirac deltas are separated by 2 square root of pi. And you combine all of these Dirac deltas, and that corresponds to your ket0 state. The ket1 state is the same thing, but it's shifted by square root of pi. So you can think of this as you're summing over all even locations, and some for ket0 and odd locations for ket1. So representing the logical states in our calculus is quite straightforward, because we allow any arbitrary functions on the labels, which means we can simply label ket0 and ket1 as with these functions, which are sum of Dirac deltas. But in practice, these Dirac deltas are not physical, and neither is summing from minus infinity to infinity. So in practice, what people use are these states with finite squeezing. So you approximate Dirac deltas with Gaussians, which have very small width. And moreover, instead of going from minus infinity to infinity, you also have a Gaussian envelope, which kind of tapers off the Gaussians that are further away. Now, if you write this in the ZX calculus, we have a very compelling picture that we can derive, which shows that these GKP states with finite squeezing correspond to the ideal ones. So look at the Z0L, which is the finite squeezing approximation. So that's same as the ideal one, but you have some injected some Gaussian noise into the into the ideal state. So you can derive this very compelling diagram for finite squeezing. And we can also reason about error correction. So you can also think about the syndrome measurement. So the circuit for syndrome measurement corresponds to this, where you have a zero logical, and you perform Control Z and you measure. And by applying some rewrites, you can derive this to be the diagram here. and we have projection at the end, which simply projects onto the code space. And to correct for the errors, we need to apply for a shift of minus n mod square root of pi. So if our Gaussian, if our GKP is slightly shifted, slightly displaced, we can correct it by applying this correction at the end. But if it has shifted too far, then applying the correction would result in a logical error.
Razin, you should,
yeah,
if possible, come to an end soon. So we have 5 minutes left for questions.
Okay. All right. So I'll quickly talk about Gaussian boson sampling, which is very important for proving quantum advantage, experimentally. So it corresponds to a circuit like this, and the reason why it's difficult is because it corresponds to calculating this quantity called the Hafnian, which corresponds to the perfect matchings of the graph. And in ZX, we have in our calculus, we have a very nice description of this Hafnian, which says that if you have an adjacency matrix for the graph, which describes the connections between all the W nodes, and if you measure ket1 on the output, that corresponds to the Hafnian. So all we need to do is show that any Gaussian boson sampling circuit like this can be written to a form that's shown before. So you prove that this is the normal form for that. And finally, to get the Hafnian, we need to simply measure, and measuring that gives us the Hafnian, which corresponds to the amplitude. And we can do all of these rewriting diagrammatically. Yeah, that's all I had to say. Thank you.
Is there any question?
Hey, great talk. I have two questions. What's the distance of the code that you showed, and how many physical qubits does it take to encode a logical qubit?
So for the GKP code, I mean you're using one quantum harmonic oscillator, so one continuous variable system to represent one logical system. But there's also a way to represent one logical into multiple wires or multiple continuous variable systems. I think so. The idea of code distance, I'm not sure how it generalizes to talking about the GKP code, because the errors here are continuous, and you're correcting for continuous error. And usually, what we do in like bosonic codes is you convert these continuous errors to logical errors. So whenever it shifts too much, it will be converted to logical error. And usually, in all of the proposals, you also have a second layer of error correction on top of this GKP code encoding, and that would correct for those errors. But I'm not sure exactly what the notion of code distance is.
I have a different question. So what is this Gaussian fragment of quantum computing that you talk about? What is the key restriction from that Gaussian quantum computing is?
The Gaussian corresponds to the classically simulable part. Oh, do you mean like what is this whole continuous variable quantum computation thing?
So I understand the definition of quantum computing, but you keep talking about the Gaussian fragment of quantum computing. What is that?
Oh, so in the continuous variable quantum computing, you have the Gaussian part, and so think of the Clifford plus T circuits. So Clifford plus T circuits in the qubit case, the Clifford is the easy part. Something that can, if you have a circuit which only includes Clifford path, you can completely simulate it easily, classically. But if you add the T gate, which could be like a resource, then it makes the quantum computing universal in qubits. So similarly, if you only restrict these Gaussian gates, which are like these ones, then stuff that can be simulated. But if you add at least one non-Gaussian gate, which is shown here, for example, any one of these, then you obtain universal continuous variable quantum computation, approximately universal. So that's the idea.
Okay. Any more question?